Now in a previous lecture we discussed a one-dimension wave equation of problem 1, which is based on the initial displacement is given of the string. Now in this lecture we discuss a problem 2 when only the initial velocity of the string is given. So what is the difference between the problem 1 and problem 2? The equation and the boundary condition are similar, only the initial condition are changed. In a problem 1, initial displacement is given where velocity is 0, and in a problem 2, initial displacement is 0, velocity is given. So only the change in a initial condition. Boundary condition which are same in problem 1 and problem 2. Now we solve a problem 2. So obviously first we solve equation 1 using a separable variable method, which is also discussed in a problem 1. So first we consider the solution form uxt is a capital X capital T. Now differentiate this equation 6 with respect to x and t 2 times. So we get del square u by del x square is x double dash t, and del square u by del t square is a xt double dash, where x double dash is a d square x by dx square and t double dash is a d square t by dt square. Now we input both value in equation 1, then the given PDE is reduced equation 7. And then we considered k, which is equal to left hand side and the right hand side of the equation 7. So we get equation 8. Now we consider 3 different cases: k greater than 0, k less than 0 and k equal to 0, and find a solution of a given initial boundary value problem for each cases. So now we first consider k greater than 0. So k greater than 0, we can take k is equal to p square, and then we get 2 OD obtained as x double dash minus p square x, which is 0. So the auxiliary equation m square minus p square is 0, so m is equal to plus or minus p. Similar, another equation where m is equal to plus or minus cp. So x of x, real and different case here also. So x of x is a c1 e raised to px plus c2 e raised to minus px, and c3 e raised to cpt plus c4 e raised to minus cpt is equal to t of t. So therefore the general solution for the case k greater than 0, we get equation number 9, where all constant c1, c2, c3 are arbitrary. Now we applying the boundary condition equation 2 in equation 9, we get c1 is equal to minus c2. And c1 is equal to minus c2 we input in 9, then the equation 9 becomes equation number 10. Now in equation 10 we apply again the boundary condition equation 3. So u is equal to 0 when x is equal to L, then we get this equation, and this equation is indicate that t of t not equal to 0, this form also not equal to 0, and we can't consider c1 is equal to 0. So therefore we can say the given equation 1 has non-trivial solution is not exist, which are satisfying the given boundary condition for the case k greater than 0. And all things we discussed in the previous lecture. Now, a case 2 we consider k less than 0. So k equal to minus p square, then the given 2 OD is obtained as x double dash plus p square x is 0 and t double dash plus c square p square t is equal to 0. And we define the solution, then the general form is uxt is equal to c1 cos px plus c2 sin px, c3 cos cpt plus c4 sin cpt, which is said to be a equation 11. Now in a equation 11, we apply the boundary condition equation 2, then we get a constant c1 is equal to 0. So we input c1 is equal to 0 in equation 11, then we get equation number 12. So in equation 12, we apply again the boundary condition equation 3, where u equal to 0 when x is equal to L. So we get 0 is equal to C2 sin PL, and this term is similar T of T. So T of T not equal to 0, C2 not equal to 0, therefore sin PL is equal to 0. And that implies we get P is equal to N pi by L. Hence, we can say the solution of equation 1 satisfied the boundary condition, which is given as uxt is equal to c2 sin n pi x by L, c3 cos cn pi by L into t plus c4 sin cn pi by L into t, equation number 13, which is again similar to the previous lecture. Now we are applying the initial condition. In a problem 1, first we apply the initial velocity, because in a problem 1 initial velocity is 0 is given. But here initial displacement is 0 is given. So first we apply the initial condition equation 4 in problem 2. That means here. So applying the initial condition equation 4, and the condition is ux0 is equal to 0 in equation 13. So we get 0 is equal to c2 sin n pi x by L into c3, because cos 0 is 1. So that implies this term is not equal to 0, so c3 is equal to 0. And c3 equal to 0, we input in a 13 number equation, then we get uxt is equal to bn sin n pi x by L into sin cn pi by L into t, where c2 into c4 is equal to bn, where n is equal to 1, 2, 3 up to n so on. So we applying the superposition principle, we get uxt is equal to summation n is 1 to infinity bn sin n pi x by L sin cn pi by L into t, which is a equation number 14. Now we consider case 3, k equal to 0. So k equal to 0, then we get two ODs obtained as x double dash 0 t double dash 0. So the general solution for the case k equal to 0, we write uxt is a c1 plus c2x plus into c3 plus c4t, which will be discussed in a, obviously previous lecture we discussed this form. So now we are applying the boundary condition equation 2, u is 0 when x is 0 in equation 15, then we get c1 is equal to 0. So therefore c1 is equal to 0, we input in a 15, we get 16, c2x, c3 plus c4t. Again we apply the boundary condition equation 3, then we get 0 is equal to c2l, c3 plus c4t, where c2 not equal to 0, L not equal to 0, and this form is nothing but t of t, and t of t obviously not equal to 0. Therefore, the non-trivial solution of equation 1 does not exist for k is equal to 0, which are satisfying the given boundary condition. So finally, the only one solution occur of equation 1 satisfying the boundary condition equation 2 and 3, and initial condition equation 4 is given by uxt is equal to summation n is 1 to infinity bn sine n pi x by L into sine cn pi by L into t. Now, the remaining one condition we apply in equation 17. That means initial condition for velocity. So obviously we differentiate equation 17 with respect to t, because the velocity condition based on the derivative of a displacement with respect to the time. So differentiate equation 17 with respect to t, then we get summation n is 1 to infinity bn sine n pi x by L into cn pi by L. Sine derivative is cos cn pi by L into t. Now we are applying utx0 is equal to fx when t is equal to 0. So we get fx is equal to summation n is 1 to infinity cn pi by L into bn into sine n pi x by L, because cos 0 is 1. So we get 18. And which is equation 18 is nothing but the half range sine series expansion of the function fx in the interval 0 to L. So therefore the coefficient bn is defined as bn is equal to 2 upon cn pi by 2 upon cn pi integration 0 to L fx into sine n pi x by L dx, where n is 1, 2, 3 up to n so on. So the equation 17 is the solution of problem 2, where initial displacement is 0 and velocity is given. So now we take one example based on the problem 2, where two ends x is equal to 0 and x is equal to pi is given for a string which is initially at the rest in its equilibrium position. So if it is a set vibrating given each point a velocity kx pi minus x, find the displacement uxt. So in this problem, given that a length of the string which is tightly stretched with x is equal to 0 and s is equal to pi whose ends, so we consider the length L is equal to pi. Also given that the string initially at the rest in its equilibrium position, that means the displacement is 0. And here initial velocity is given kx pi minus x. And we want to find the displacement uxt. So here given that length L is a pi, displacement 0 and velocity is a kx pi minus x is given. So the initial boundary value problem is defined as, this is the equation 1, one dimension wave equation, boundary condition are similar, only L is replaced with pi and the initial condition displacement is 0 and the velocity is a kx pi minus x. So the given problem is similar to the problem 2. So therefore the solution form is uxt is summation n is 1 to infinity bn sine nx into sine cnt. Why we write this form? Because here we consider the length L is equal to pi. So sine n pi x by L, L is pi, so pi cancel. So the form is sine nx and similar sine cnt, where we find the value of bn. So bn is equal to 2 upon cn pi 0 to L fx into sin n pi x by L dx. So 2 upon Cn pi, length is pi, so 0 to pi, kx, pi minus x is fx sine n pi x by L, L is pi, so pi cancel, sine nx dx. Now k common, so 2k upon Cn pi, the remaining term is pi x minus x square into sine nx. So we integrate this both function using the integration by part. So pi x minus x square we consider u and sine nx we consider v. So this is the solution form. So u as it is, integrate of sine nx is this. Now differentiate this bracket is this, integrate this bracket is this. Now again differentiate of this bracket is minus 2 and integrate of this bracket is this. And the limit is 0 to pi. Now x is replaced with pi, upper limit. So pi square minus pi square, this term is 0. Sine n pi is 0. So again this term is 0. So both term is 0. Cos n pi is a minus 1 is to n. So the upper limit is minus 2 minus 1 is to n upon n cube. Lower limit, so this is 0. Again sine 0 is 0. Minus n minus, so plus cos 0 is 1, so 2 upon n cube. So we get the Bn is a 4k upon C pi n raised to 4, 1 minus 1 raised to n. Therefore, the solution of the given problem is uxt is equal to, we input this value here, so n is 1 to infinity, 4k upon C pi n raised to 4, 1 minus 1 raised to n sine nx into sine cnt. So this is the solution of the given example. Now we discuss a problem 3 of one dimension wave equation. Problem 3 is based on when both initial displacement and initial velocity of the string is given. Problem 1 only displacement is given, problem 2 only velocity is given, and problem 3 both are given. So the mathematical modeling of this type of problem is defined as one dimension equation, wave equation, equation 1, 2 and 3 boundary condition is similar for all problem. So 2 and 3, and the initial condition, displacement we consider one function fx and velocity we consider another function gx. Now solution of this problem is nothing but we define with uxt. So uxt is equal to u1xt plus u2xt, where u1xt consider as the solution of problem 1, where initial displacement is fx and velocity is 0. So u1xt is the solution of problem 1 type, and u2xt is the solution of problem 2 type. And then we add both, then we get the solution of problem 3 type. Okay, so again the problem 3, where initial displacement as well as the initial velocity is given. So we write uxt is a u1xt plus u2xt. u1xt is the solution we consider problem 1 type, and u2xt we consider the solution of the problem 2 type. Okay, so in all lecture application of PDE, we discuss separable variable method, one dimension heat equation. We discuss in a one dimension heat equation 2 type of problem, homogeneous boundary and insulated ends. Then we discuss one dimension wave equation. There are 3 types of a problem we discuss. One, where initial velocity is given. Second, sorry, initial displacement is given, second problem velocity is given, and problem 3 where both are given. So now we complete a topic application of a partial differential equation. So thank you. Thanks to all students. And if any query, so please contact me. My email ID is Harshad Patel .ash@svitvasat.ac.in. Thank you.